So hello and welcome back. So in this video we want to do a couple of experiments with actually not a couple of experiments, but an experiment with basically inductors. And we had basically two types of circuits that we could make with inductors. Basically, they are both called RL circuits, and these RL circuits are the basically voltage dividers for AC signals, and you can have an inductor and a resistor in series, and then well, as you know, you have some output voltage that can be measured across either the resistor or the inductor, as we have done in the previous theory videos and experimental videos. And but you know, the problem is that I have actually done this I have done this experiment a couple of times. I mean, I have done a couple of experiments a couple of times before, related to these inductors, and it's hard to get an opinion on, or it's hard to basically, it seems to be hard to figure out how these inductors are behaving, especially in different frequencies. Now that could also partly have been due to the fact that there might have been something wrong with my test setup. That I had a function generator and an oscilloscope. They are kind of sometimes not giving you consistent results, and but now what I want to do is that I want to perform the same experiments using this setup over here, this function generator. It goes all the way up to probably 2 megahertz or so, which is, I mean, I cannot go any higher than that for now. And using this oscilloscope. This oscilloscope is not bad, it's okay, and it gives you good results, like 99% of the time, so 98% of the time, except for the time that it doesn't work or it gets confused, in which case you have nothing to worry about, because you know that it's not working properly. But on this oscilloscope over here, the problem is that on this one, these buttons over here, these buttons and some of these controls are kind of worn out. Okay, so for example, I have noticed that when I'm basically measuring something on this oscilloscope, if I happen to, for example, if my hands happen to get, I mean, if my hand happens to basically to push one of these buttons like this, for example, accidentally, then the signal keeps jumping up and down, and it stays there. It's not that it keeps jumping up and down. If I touch any of these buttons, not touch, just touch them like that, the signal keeps jumping up and down, and all of a sudden sometimes it stays there. So I would not probably, and that's the problem with this oscillator. So you cannot really trust it. Although it's a very good, sturdy oscilloscope, but this front end is probably out of order, and I think the trigger circuit the trigger circuit on this oscilloscope might also be out of order. So it's just not, I mean, I'll have to get rid of it probably, although I like it very much. But I'll have to get rid of it and get a better oscilloscope. Probably, I don't know. That's something that I'll have to decide later. For now, let's get to this experiment. So I'm going to bring you over here. So I'm going to bring you over here, and we will do this experiment together. So what I'm going to do is I'm going to first try the low pass filter, and just to give you some idea of a low pass, in case you have forgotten that, a low pass filter, a low pass RL circuit is basically something like this. Let me show you what that is. So a low pass RL circuit is something like this. So you have basically an inductor over here. You have an inductor over here, and this inductor is connected in series with the resistor. This resistor goes to ground. This is where your signal comes in, and this is your V of out. Okay, so this is your L, this is your R, and this is a low pass filter. This is a low pass filter, and the signal on this, the voltage versus frequency curve of this circuit would be something like this. If this is V of out and this is F of in, you're going to get some signal like this, and you see at low frequencies much of your signal is passing through. At higher frequencies, much of your signal is going to be suppressed, and that's basically why it's called a low pass filter. And why that happens is that basically this V of out that you have here is actually the output voltage across this resistor, and at low frequencies the reactance of this inductor is actually very low, right? Because it has a direct relationship with your frequency. X of L is equal to 2 pi FL. So there is a direct relationship between frequency and the reactance of your inductor. So since that's the case, then at low frequencies there is low voltage drop across here and high voltage drop across the resistor, and then when the frequency is high, then you have the reverse of this situation. So when you have high frequencies, high voltage drops across here and low voltage drops across here. So at higher frequencies the voltage is going to be much lower, and that's basically the shape of the V of out versus F of in of this circuit over here. So now what I want to do is that I want to build this circuit, and I have built this circuit this way, meaning that I didn't want to do it on a breadboard, because you know, basically a breadboard is practically, I mean, a breadboard, when you have all of these rows that are connected. Okay, so all of these rows are practically inductors. So to get better results, I wanted to I just connected this resistor directly. I soldered that resistor directly to the end of this inductor, and the value of this inductor is 100 microhenry. and the value of this resistor is 1 kilo ohm. Now, in order to have better results here, what I will do now is first measure the resistance of this resistor, because there is tolerance of this on this resistor. So if I measure the resistance of this resistor, it's basically it is 988 ohm. Not 1 kilo ohm, but 988 ohm. So your R is equal to 988 ohm. And I'm assuming, although I don't really know, and I don't have any inductor meter here, and I'm planning to build one once we are done with these experiments. If we can make sense of how these inductors are behaving, then based on that we can build a test circuit using some signal generator and an oscilloscope. Then that way you can figure out, for example, if you have some inductor, you don't know the value of the inductance of that inductor, then you can figure out that value if you have a signal generator, an oscilloscope, a test setup, and you have to do some calculation, and then you get the value of the inductance of your inductor. That you can do, but first you need to be able to make sense of how these inductors actually function. But of course, when you have an inductor meter, it's always easier, because you don't have to do the math, you don't have to do the calculation, you don't have to connect it to an oscilloscope and signal generator and test setup and the whole thing, and you just connect it to a connector on your meter, and then it gives you some number. But we don't have it right now, but it's not a problem. It's actually fun to build the circuit and see how it actually functions. Okay. So now let me connect this to my to a signal generator and connect it to an oscilloscope. See how we'll take a look at the input waves and see what it turns out to be. Okay, so now what I will do is that this is basically the output of the signal generator. I connect it to, this is basically the output. This is ground. So the output I connected to the end of the inductor, and the ground I connected to the end of the resistor. So this is, if I basically change the order of this, then I will basically build the other circuit. That would be a low pass filter, not a high pass filter. So now this way, if the signal comes into the inductor, then you would have a low pass filter. Otherwise, you would have a high pass filter. And then the oscilloscope, and then I connect this thing over here, so I can read the frequency. I can read the frequency on this counter. Okay, and this is the signal generator. I go to about 0.2 times 1. So this must be about 1 hertz. This must be about 2 hertz or so. Okay, so this is about 2 hertz. And then if you connect this to this oscilloscope, you set these to the AC coupling. Okay, and set this to, for example, 510 volts, and then this is on normal channel 1. So I'm triggering on channel 1, and my I go to dual mode to see both channels over here. And if I connect channel 1 to my input, which is basically the input signal coming here, so this is the input signal. Excuse me. Okay, so input to there, and then my output I connected to channel 2, and then I must have some sort of signal over here. I don't see anything yet, and the frequency is too low, so the oscilloscope cannot really do much there. But that's basically, if I ground this and go to auto, if I ground this thing over here, not seeing anything. Okay. Move this up here, and if I increase the frequency a little bit, for example 10K, so now I can see something. And if I ground this thing, okay, so now if I ground this thing, I can bring it up here. Okay, and now my output signal is about 10 volts peak to peak. About 10 volts peak to peak. And just to make sure that, although I'm pretty sure about that, so I don't have to do much there. So now you can see that my output is also about the same voltage, 10 volts peak to peak, but now the frequency is about 20 kilohertz. Okay, so now I can go down to about 2 hertz or so, and you see that the output is just about 5 volts peak to peak, meaning that when the frequency goes that low, about 2 hertz or so, the voltage goes low as well, the peak to peak voltage. Or it might be something related to this signal generator. I don't really know, but I can now, this is about 20 hertz right now, and now I have the peak to peak voltage of about 10 volts peak to peak. Okay, so now what I want to do is actually find the frequency where basically the voltage doesn't plummet to 5 volts peak to peak, and so on and so forth. So I basically go down here, and now it's around, it must be the frequency must be around 2 hertz or so, and my output is at, you see over here, the output is at about 5 volts peak to peak. So I increase the frequency, and now my output is at about 10 volts peak to peak. About 10 volts peak to peak. Okay, so now Now the frequency is about 315 hertz or so. Okay, so if I go down here, the output is still about 10 volts. Okay, so we can start at about this frequency, whatever that is. Although we cannot really read it. We cannot really read it. It's actually very low, meaning that if you take a look at the, see what happens here. Go a little bit higher. So it's about, for example, 1, 2, 3, 4, 5, 6 times 50 is equal to 300 milliseconds. So that's about 300 milliseconds. So 1 over 300 milliseconds would be about 3 hertz or so. Yes. So that's a frequency where we have the output, and so we will start at here. Okay. Now you see that the output, of course I cannot trigger on anything right now, but we will get past this stage pretty soon. So you don't need to worry about the fact that you cannot see much right here right now. So so now while I'm doing this experiment, I'm going to actually write down some data from here. So basically I know that my VF in is supposed to be around 10 volts peak to peak. And that's 10 volts. And then this is my, I wrote down my frequency as well, and that's about 4 hertz right now in hertz. Okay, and then I have my VF out as well. So let's see what we get. So right now the input is at about my input is at about 1.4 times 5 is equal to 1.4 times 5 is equal to 7 volts peak to peak, and my output is at the same voltage, basically about 7 volts peak to peak. Okay, 7 volts peak to peak, 7 volts peak to peak. Now if I increase the frequency to something like 6 hertz, the voltage does not change much. Okay, if I go about for example probably 8 hertz if I'm not mistaken, and now I'm getting closer and closer to somewhere 1.8. So at about 8 hertz, the voltage, the input voltage is at about 1.8 times 5, is about 9 volts peak to peak and 9 volts peak to peak output. If I get 2, this is 1, so 1, that's about 10 hertz, the frequency, and you see your output is about the same, thing, 1.8. So that's 10 hertz. The output is about 9 volts. If I go over to 12 hertz or so, the output is at about the same thing. 12 hertz would be 9 volts, 9 volts. About 14 hertz, the output doesn't change much. 18 hertz. At 18 hertz, your input is at about the same voltage, output about the same voltage, and about 20 hertz doesn't change much. Okay, now right now I'm at 20 hertz, so I could multiply by 10 and go back here, and still I'm about 20 hertz right here. So now times 100, so now this is about 40 hertz. Not much change here. About 60 hertz. Not much change here. About 80 hertz. About 80 hertz. About 80 hertz, my output is at about 10 volts peak to peak. Okay. Now, this is about 100 hertz. Not much change. About 1.2 times 100 is equal to 120 hertz. Not much change. 160 hertz, 180 hertz, not much change. 200 hertz, not much change. Multiply by 1K and then come back here, not much change. This is 400 hertz. 320 hertz. I don't know if the scale over here is wrong. You see over here we are at about 1.4 times 2 milliseconds, 2.8 milliseconds. 1 over 2.8 milliseconds, 357. Okay, 357. Okay, so the frequency is about 357 hertz, and the counter is telling me it's 324 hertz. So at about this frequency, not much change. Not much change here. not much change in the output, not much change in the output, not much change in the output, not much change over here. So okay, so now I'm at 0.2 times 10k, which is equal to 2 kilohertz or so. Not much change in the, although my input is kind of changing. My input is kind of changing. Okay, so now go to 100k and come back here. Not much change I can see over here, and to 1 megahertz. Come back here, and you see over here what happens is that at this frequency everything seems to be okay. So I'm going to go to 100k, and somewhere over here at this frequency, so this is about 0.2 times 100k, which is equal to about 14 kilohertz or so. At about 14 kilohertz, my input and output are still the same. 10 volts, 10 volts. 14 kilohertz, 10 volts, and 10 volts. Okay. Now, if I increase the frequency over here, you see still nothing is happening much, but at 2 times, basically at 200k, still not much is happening. Now at this frequency, 200k, at 214k or so, that you see the output is slightly higher than the input. At 200k, so that's the, here is 10 volts and this is 10 volts, so here the output is slightly higher. Okay, now if I increase the frequency here, for example, right now I'm at 0.2 times 1 megahertz, which is basically 200 kilohertz, right? So if I increase the frequency here, you see the input is actually not, and this is your output. Your output is my input is about 10 volts peak to peak. My output is about, you see over here, that's 2.2, 2.2, 2.2, 2.23, 2.22. That's 2.22 times 5 is about 11.1 volts. 11.1 volts at around 500 megahertz, 500 kilohertz, I'm sorry. 500 kilohertz, my input is slightly above 10 volts. I take it as 10 volts. Output is 11.1. 11.1 volts peak to peak. So now if I move to, for example, around 900 kilohertz or so, about 1 megahertz, the output is at about 1.4 times 5, which is about, I'm sorry, 2.4 times 5. 2.4 times 5 is about 12 volts peak to peak. That's about that's something about 950 kilohertz, and the input is still at 10 volts. Okay, and remember that we are actually we are basically what we are doing is that we are measuring the voltage across the resistor. At channel B is across the resistor to ground. Okay, so now I increase my frequency to, for example, 1.1, 1.2 megahertz, and the output is still, see over here what happens. So right now I'm at about 1 megahertz, okay, and my output is at about 12 volts. Now what happens is that there is a spot over here where the output is right here at 1 megahertz or so, right this point. Okay, at this exact frequency is the highest amount of output that you can get, and of course this counter is sometimes lying to me, so I want to basically I want to basically measure the frequency over here manually. Okay, so I put this over here, center over here, and in order to measure the frequency, you actually need the period of this waveform, which is basically from this point all the way up to this point, these 2 points. If you have a better oscilloscope, you could have those 2 cursors, and then you can bring the cursors down to any point on your waveform, and it would tell you, for example, from this point up to this point you have so many, for example, seconds or milliseconds or microseconds. But over here everything is pretty much manual, so we have to do a lot of math here. So over here you see I want to measure from here. I want to measure from here, right from this line, and I have intentionally basically adjusted everything to this line, starting from this line all the way to, for example, some place over here, somewhere over here. So 1, 2, 3, 4, 5. So 4.85. I take it as 4.85 horizontal units. 4.85 times my time base, which is equal to 0.2 microseconds. 0.2 microseconds. And if I take the reciprocal of that, it's 103. That's 1,030,000. That's 1 megahertz. That's 1 megahertz. So the number that you get is basically 103092728. 1030928. That's in hertz, right? Now in order to to basically convert that to megahertz, you have to divide by 10 raised to the power 6. So you get 1.030928 megahertz. Okay, and I take it as 1 megahertz. Okay, so at 1 megahertz, this is the peak of that output voltage. My output is about basically 2.4 vertical units times 5 volts, which is 12 volts. And from this point on, the voltage starts dropping. Okay, so this is the peak, and then you can increase the frequency here. Go to, for example, somewhere about over here. This is 1.2 megahertz. This is, for example, and you see that the output voltage is actually dropping. So okay, so you see that at 1.2 megahertz, for example. Now let me actually basically measure this thing over here as well again, and see if the counter is lying to me or not. And I take this as the right measurement, and then compare it to the frequency that thing is telling me. So let me put this over here, and then this is 1 2 3 3 1 2 3 4 move it over here a little bit. So as you can see, this is my output signal, this one. So this is you have to measure from this point all the way to this point. So this is 1 2 3 4 4.2 horizontal units. Okay, so 4.2 horizontal units is going to give you 4.2 times 0.2 times 0.2 microseconds, and take the reciprocal of that, it's 1.2 megahertz, 1.17, 1.19. Okay, it's good. The calculation is giving me 1.19 megahertz. The counter is giving me 1.17 megahertz. So at these high frequencies, it seems to be having no problem. So at 1.2 megahertz, the output is at about the same thing, 12 volts, and the input is at 10 volts. Now if I increase the frequency, you see that the voltage is dropping. At this point you're at about 1.95 times 5 is equal to about 1.95 times 5 is equal to about 9.75 volts. Or so at 1.5 megahertz, you are at 9.75 volts. The input is at 10 volts, the same thing. So right now that the output is dropping, so if you come over here, you can measure this thing as so this is at 1.5 times 5. 1.5 times 5 is equal to 7.5 volts peak to peak. 7.5 volts peak to peak at 1.8 megahertz. The input is still at 10 volts or so, and at about 2 megahertz my output is dropping to 1.2 times 5, which is equal to 6 volts peak to peak. Basically 2 megahertz, 10 volts and 10. Okay, so now this is all the way up to 2 megahertz. Okay, so now what I want to do is that I want to I have another signal generator that can go all the way even up to 4 megahertz or so. So let's take the rest of this experiment. I said that the other signal generator I start from 2 megahertz from the other signal generator, and we go all the way up to 4 megahertz or so, I mean as high as we can, and we see what happens at basically at some higher frequencies. Okay, so now I will move into this signal generator here, and I will go all the way up to 900 kilohertz. Okay, 1 megahertz. Okay, now if you take a look at the output of this signal generator on this oscilloscope here, let's see what we see. So first of all, I connect and you can see the frequency over here. I change over to the other signal generator. So let me take care of my. Okay. So I change over to the output of the other signal generator, and it must be around 1 megahertz. So I'm about 1 megahertz, and I'm sorry, I have to start at 2 megahertz. So, but let's take a look at the output first, and then we will see what we have over there. Okay. So the output here is some output like this. Let's see. So this is negative. This is positive. And you see this is 10 volts peak to peak, exactly the voltage that we want. Exactly 10 volts peak to peak, and the frequency is at let's see, let's take this at 1, 2, 3, 4, 4.8 times 0.2, 4.8 times 0.2 microseconds into 10 raised to the power negative 6 seconds, and take the reciprocate of that, you will get 1.04 megahertz. Okay, you get 1.04 megahertz. Now the problem with this signal generator is that if I increase the frequency, as you can see over here, all the way up to even here, I have the problem. you see over here the output above 1 megahertz. I have no, at 1 megahertz I have my output, whatever I set it on the signal generator, it's basically that output. Now if I increase the frequency, you see the amplitude is decreasing, I'm sorry. And now I'm at about 2.5 megahertz or so. Now it's still decreasing, and even the waveform is kind of getting deformed. And you see over here what happens. So it's basically good for nothing. And basically the last reading that I had on this circuit was about 6 volts output at 2 megahertz. 6 volts output at 2 megahertz. Okay, so what we can do, is still do the experiment anyway, okay? But we won't, we will have to keep track of the input signal as well, okay? So now what I'm going to do, I'm going to set this to 2 megahertz, and you see this is, the output is set to, for example, something like 10 volts peak to peak. At one, I'll set it to 2 megahertz. I'll set my output to 2 volts peak to peak, and then I will do the experiment. But like I said, we'll have to keep track of the input and both the outputs. Okay, so and the waveform gets a little bit deformed, and the same thing will happen on the output again, which is not a problem. You will get the same waveform as you have on the input and the output as well, so that's not a problem. So now I'm going to connect the input of the signal generator to the excuse me, to the circuit. I will connect the channel 1 to input. I connect channel 1 to input. Channel 1 to input. And channel 2 to output. And you will have this waveform over here. So now at about 2 megahertz, now let me somehow get some data over here as well. So now at 2 megahertz, what I have is at 1.96 megahertz, about 2 megahertz, what I have is my input is at 10 volts peak to peak. My output is at about 1.45. So 1.45 times 5 is equal to about 7.25 basically peak to peak, or so about 777 volts or peak to peak, which is about the same thing that we had before. Now, if I move this to, for example, 2.5 megahertz, you see I have still about the same input about the same input, but my output is at 0.8 times 5, which is equal to 4 volts peak to peak. So at 2.5 megahertz, my input is 10 volts peak to peak. My output is 4 volts peak to peak. And at let's go to 3 megahertz. Let's see what happens at 3 megahertz. 2.99, 2.89, 2.9. The output drops to 0.6 times 5 is equal to 3 volts peak to peak. I seem to be having kind of the same input, but now the input is 1.8 times 5. So 1.8 times 5 is equal to 9 volts. And I'm at 2.9 megahertz. 2.9 megahertz. Okay. Now, if I move to, for example, 4 megahertz at 3.84 megahertz, at 3.994 megahertz, my input is at 1.6 times 5, which is 8 volts peak to peak, and I'm at 3.4 megahertz, and my output is at 1.2, let's say, times 1 is 1.2 volts peak to peak. Okay. And what I can do, I can keep increasing the, I can even do something else. I can keep increasing the input, the input amplitude, to get it to 10 volts every time I want to make a reading. Okay, so I go back to 2.5 megahertz. Okay, and now my input is at about somewhere below 10 volts. So I move it to, so you see these are interdependent, right? So now I make it basically 10 volts peak to peak, and now I can make a reading based on what I was doing before. So it's 1, 2, 3, 3.4 times 1 is 3.4 volts. 3.4 volts. Okay. At 2.5 megahertz, input 10 volts, and this is 1, 2, 3, 3.5 volts peak to peak. 3.5 volts peak to peak. At 2.9 megahertz or at 3 megahertz, at 3 megahertz, I make my output 10 volts peak to peak. So I really need to think about, okay, so 10 volts peak to peak, and then measure over here what sort of output I have. This is 2.4 times 1 is 2.4 volts. Basically that is 10 volts peak to peak, and that's 2.4 volts peak to peak. Okay, at 4 megahertz, at 4 megahertz, if I make some changes to my output, my input is now at 1.4, so 1.4 volts peak to peak. Okay, at 5 megahertz, at 5 megahertz my output is at a little bit below 1 volt peak to peak. At 5 megahertz, 10 volts peak to peak, 1 volt peak to peak. At 6 megahertz, of course it's no sine wave anymore, but you get some idea. So it's 0.6 volts, 600 millivolts peak to peak. If you move to 7 megahertz, it's somewhere about 0.5 volts peak to peak. 0.5 volts peak to peak at 7 megahertz. At 8 megahertz, you're at something about 0.4 volts peak to peak at 8 megahertz. At 9 megahertz, you're at about 0.25 volts peak to peak. 0.25 volts peak to peak at 9 megahertz. And at 10 megahertz, you're at about 0.2 volts peak to peak. Okay. So that's basically how this thing is behaving. Now in the next video we will do some analysis of this data, and we will do some calculations to see basically. And one more thing that we actually did not do, we actually do need to get some data about the phase shift as well. Okay, so let me get the data about the phase shift as well, and then we will move to the next stages of this experiment. So I will end this video here, and in the next video we will get some data for the phase shift, and then we will see about the rest of this thing. I'll see you in the next video.